The question I have is, what effects does flowing water have on geotechnical design of structures? So let's start with the effect of water in soil on geotechnical engineering design. Let's talk about static water first. Static water introduces a pressure called hydrostatic pressure, which exerts a force on structural elements that are underground and in contact with water, like, for example, a sheet pile wall. These additional forces need to be considered in the design of structures. The hydrostatic pressure also changes the stresses in soil. Usually, as the hydrostatic pressure increases, the shear strength goes down, which in turn affects the stability of the structure. The physicochemical properties of clays, like cohesion, depends on the presence or absence of water. Water introduces capillary forces, which also has an influence on the behavior of the soil. In addition to all these effects that we have in static water, we have some additional effects to be considered when you have seepage of flowing water. For example, pressure in the water could either increase or decrease from the hydrostatic pressure. This change affects the equilibrium of the structure, sometimes in an adverse manner. The change also could lead to the formation of quicksand or piping failure. When you have seepage, water is flowing from one point to another, which usually gives you problems. For example, when you are carrying out an underground construction, water could flood the construction area, preventing you from continuing the construction. When you build an earth dam, your intention is to retain the water on one side of the dam. But certain amount of water is always lost by seepage through the dam. You, as a geotechnical engineer, will have to come up with ways to control these. Let's consider some examples of seepage problems. Here I have 3 examples. In the first example, a concrete dam is built to retain water on the left side of it. And in the second example, an earth dam serves the same purpose. In the third example here, an underground construction is being performed. 2 sheet pile walls have been driven into the soil in order to facilitate this. Let's come back over here and consider the concrete dam example first. This concrete dam is built on soil, and soil is usually much more permeable than bedrock. So what happens is water seeps through the soil from the left side to the right side. Specifically, let's just say I take a water molecule that starts from this point right there and follow its path. It's going to follow a path that looks like this. Something like this is called the seepage line. So this is how the water is gradually lost from the upstream side to the downstream side. So normally there will be a little bit of tailwater here. So what are some of the design issues here? Number 1, we need to know the rate at which the water is lost from the upstream to downstream by seepage through soil. Let's say the volume rate is Q. We need to calculate this in order to control this. Number 2, in this region over here, because of the increased water pressure due to seepage, there's a potential for the formation of quicksand. This usually happens in a sandy material. What happens is the saturated sand could turn into more like a liquid. When that happens, the sand particles could be gradually scoured away from this toe region, and before you know it, there could be a large cavity here which could lead to the collapse of the concrete dam. And this type of failure here is called the piping failure. Number 3, due to increased water pressure at the bottom of the dam, you have a resultant uplift force like this. If this uplift force is too much, it could lead to failure of the dam. Let me show you a short video on the Austin Dam failure in Pennsylvania. This apparently happened because of uplift force. Now let's talk about the earth dam example. In this example, the earth dam is built on a bedrock, and the bedrock is a lot more impermeable than the earth dam, and therefore the water is going to be flowing through the dam. Now let's consider a water molecule that starts from a point like this. And we'll see later that this water molecule is going to start off perpendicular to the face of the dam over here. And then it's going to be flowing like this to the downstream face of the dam. One that starts from over here is going to go like this. So these are two of the infinite number of seepage lines we have here. So what are some of the design issues? Number one, just like in the case of concrete dam, we want to know the rate of seepage, Q. Number two, because the water is coming out at a certain velocity in this downstream phase, it could cause erosion, which could eventually lead to failure. Number three, the possibility of slope failures. We know seepage changes the water pressure, right? And sometimes this change in water pressure could decrease the shear strength of the soil, which could lead to slope failures of either the upstream side or the downstream side. Finally, neither the earth dam nor the bedrock are perfectly homogeneous. There are always weak zones in the earth dam and cracks and fissures in the bedrock. Water has a way of finding these features and flowing through them. As it does, it causes erosion and small holes become bigger and eventually the whole dam fails. In 1976, Teton Dam in Idaho failed, and the cause of failure is considered to be piping. Let me show you a short video on that. Now let me take the third example, the sheet pile wall example, and point out the design issues. Number one, because of the differences in the elevation of the water table and the bottom of the construction area, water is going to be flowing from the water table into the construction area like this. So like in the other examples, we need to know the rate of seepage Q. If we do, then we can pump the water out to keep the construction area dry. I'll show you some pictures on that in a second. Number two, there is now an unbalanced water pressure on the sides of the sheet pile wall. This needs to be considered properly, otherwise the wall could fail. Finally, as in the concrete dam example, there's a potential for the formation of quick condition in this area, which could cause failure of the wall. Let me now show you some pictures showing flooding of the construction area and how pumps can be used to keep the construction area dry. In this picture, you see water here in the construction area, and then using this method called well point dewatering, the construction area has been dried up. So just to summarize, I showed you three examples of geotechnical structures and pointed out some design issues that arise as a consequence of water flow.